Okay, many thanks. It's a great pleasure to be here. Many thanks for the organizer and especially to Bary. In fact, my talk is very much connected to Sergio's beautiful presentation. Okay, but rather than comparing tools, I will compare concept. Okay? So. So we compare two basic concepts of min-max value and equilibrium points in terms of definition, property, interpretation, the tools, and main development. Okay, and in particular, I will question the approach, saying that value is a particular case of equilibrium points, and equilibrium is an extension of the value to n% games. So basic concept, value, the min-max theorem allows to evaluate an interactive situation of pure conflicts by a number, the value of the game. So you have function f on a product set, and it corresponds to a 2% zero-sum game, where the strategy set of the player is x and player 1 is x, payoff f for player 1, and y and minus f for player 2. So you define two concepts, the sup-inf and the inf-sup, okay, which sup-inf is the largest amount that player 1 can guarantee, and inf-sup is the dual notion. And the min-max theorem is a condition on the triple x, y, f for these two quantities to be the same. Okay? An associated notion is the duality gap. Okay? And so an equivalent formulation takes the form of if for every y there is an x such that the payoff is greater than a, it means that there is an x such that for every y you can get a. Okay? And we call epsilon optimal strategies, strategies that satisfy f of xy greater than the max min. Okay? So all these concepts are defined in a unilateral way, okay? Meaning that epsilon optimal strategy of player 1 doesn't depend on the way player 2 is behaving. Equilibria is well known, okay? You have the strategy game, find a set of players, strategy, Nash equilibria means there is no profitable deviation, and alternatively, you can say that there is no strategies that will be destabilizing this notion, okay? So the minimal hypothesis to sustain equilibrium concept is the following. First, the profile has to be public knowledge. Okay. Public knowledge means the same for all. Okay. So second, each player knows her best reply correspondence, and each player is rational. So one scenario is the following: a profile is suggested to all players, and each player plays the recommendation or his component, if and only if it's the best reply, given the n-1 tuple of the other. Okay? So at this level, no players know whether the suggestion is an equilibrium or not, and there is no notion of credible threat since player I doesn't know the payoff function of player J. Okay? So what I want to emphasize here is that in the definition and to justify Nash equilibria, okay, you have just to know S and your payoff function. Okay? So in particular, there is no reason that the player should know that this is an equilibria, or whether they will be they will have an idea of whether the other will apply or follow the recommendation. An alternative approach is say that assume that one player intended to play SI. If he knows S, then he will not change his mind or plan. So you have two interpretations. The first one is proposal, which means that the only acceptable public proposal are equilibria. Okay? If it's not an equilibria, then at least one of the players will not follow the proposal. Okay? And the second one is a norm, so it's very related to what was said about Nash interpretation. So you have a dynamical process and then some norm of behavior, and there is some convergence of this dynamical process. So in this case, it can converge only to an equilibria, okay? And moreover, if in this case, the player, assuming that the other are rational, will deduce that what is played is an equilibrium. But this is much more general than this interpretation because it applies to, for example, biology, where there is no question of rationality. It's just that it's consistent with the best reply. If you modify the information of the player concerning the other player's characteristic, then the justification of equilibria change drastically. So this is an example of a game. You see player 2 is dummy. So player 1 chooses to give 0 or 1 to player 2. Okay? So the equilibrium manifold is just the best reply correspondence of player 1 to the move of player 2. But you see that there is no reason for player. So if player 2 is a dummy, and if player 2 knows the payoff of player 1, okay, then he would like to play left, okay, so that player 1 will play bottom. But for this, he has to know that player 1 knows that he, player 2, knows the payoff of player 1. Okay? So if player 2 knows the payoff of player 1, it's not enough. But if player 2 knows that player 1 knows that he, player 2, knows the payoff of player 1, there is no reason why player 2 should play right. And the only equilibria will be left, or in fact, it's a part of the equilibrium component where the probability according to which player 2 plays left, okay, is such that the best reply of player 1 will be bottom. So you see here you have a notion, a selection of equilibria that depends on things that do not appear in the definition of equilibria, namely the information that you have about the other payoffs. The other player payoffs, okay? And here it's at the second level. Player 2 should know the payoff of player 1 and should know that player 1 knows that he, player 2, knows the payoff of player 1. Okay? So here there are three different issues given an equilibria. So first one, whether the player knows that it's an equilibrium. Usually it's not the case. I mean, unless you know the payoff function of the others. 2, whether it will be played. So this is a question of rationality. And then how come that this equilibria emerge? Okay? So it's quite different from the standard hypothesis under which the equilibrium concept is used, where usually we assume, or it's assumed that there are common knowledge of the game parameters, common knowledge of rationality of the player. And then the main issue is the choice of an equilibrium. But even in this case, even in the case of uniqueness, the justification of an equilibrium is problematic. So this was the example of Human and Nash that has been already discussed several times. Okay? The point here is that the Nash and value are the same, okay? But equilibrium strategy do not guarantee the min-max value, and optimal strategy are not in equilibrium. Okay? And in this paper by Human and Nash, they said that it seems to them that the min-max, I mean the optimal strategy will be preferable to equilibrium strategy. Okay. So commands, value is a number, equilibrium is a profile of strategy, and the main property is that if a zero-sum game has a value, then epsilon optimal strategy form a 2 epsilon equilibrium. Okay? And the specificity of zero-sum game is that you have uniqueness of equilibrium payoff, which is the value, exchangeability of the strategy, And this is based on the unilateral formulation, namely you don't have to anticipate any move of your opponent. Okay? And then you have a duality property. So what are the tools? The tool, the value, for the value, the first proof of the min-max theorem in the finite case is due to von Neumann in 28. But it's amazing if you look at the proof, what he proved, actually, it's a saddle point for the function. Okay? So he's using a fixed point theorem. And the first proof using separation, which is the tool that is needed in this case, is due to Jeanville, who was a student of Borel, and it appeared in 38. Okay. And the modern alternative proof of the min-max theorem, there were plenty of alternative proofs. The simplest will be in the finite case by induction on the size of the matrix, it's due to Loomis. And otherwise, you have Fourier elimination, alternative lemmas. This is in finite dimension, or duality for linear programming. In Rn, you can use separation of convex set, and it's the same proof in the Hilbert space, but you're just using the projection on the closed convex set. Okay? And then you have a unilateral procedure in discrete time, so this is approachability, Blackwell theorem. Continuous time dynamics, this was already done by Braun and von Neumann. You look at the ordinary differential equation and you prove that the accumulation point will be optimal strategies. And then you have fictitious play in discrete and continuous time, Braun, for Robinson, and so on. And then replicator dynamics or more general, no-regret dynamics. Okay? So general formulation is Sion theorem, okay? When you have two sets that are compact subsets of topological space, and one of the two is compact, you assume that the function is quasi-concave and upper semi-continuous with respect to x and dually for y, then there is a value. Okay? So you have geometrical and topological assumption on the set and on the function. Okay? And the basic tool is the Hahn-Banach separation theorem via, for example, the intersection lemma. For equilibria, so the first proof of existence for finite games was using Nash maps and Brouwer's fixed point theorem. So that map was already recalled by Rida. And general version will be you have a compact convex subset of topological vector space, and the pair function for each player is quasi-concave with respect to its set of strategy, and continuous, okay? Then the set of equilibria is compact convex. So the proof relies on Kakutani, and again you have geometrical and topological property, and the main difference is the joint continuity. Okay? So in the min-max theorem, the pair function is continuous with respect to x or y or upper semi-continuous. Here you need joint continuity. Okay, so now I will just describe briefly research direction and advances in the theory of equilibria and for the value, and then comment. Okay, so here I will just choose four fields for equilibrium. One is selection, okay, so equilibrium selection. So this has been extremely active, okay, starting with Selton and the Nash, because then you have a proper sequential persistence table and so on and so forth, okay. And the point is that you have two directions. One is by a collection of example and interpretation, and this is basically based on the fact that you assume that you know the strategy of your opponent, and you will interpret his strategy or potential deviation. Okay? Note that all this is absent from the definition of equilibria. Okay? In the definition of equilibria, you have just a profile, and it has to satisfy some inequalities, okay? And there is nothing about the fact that the player knows or not the strategy of the opponent, okay? And in fact, there is a big difference for me between elimination of a weakly dominated strategy, which is related to index, we'll discuss this later on, and subgame perfection, where for subgame you need to use the fact that you know that the game is an equilibria and you identify subgame, which are concepts or ideas that are not in the definition of equilibria. Meaning that an equilibria in the game where the player knows, all the player knows the strategy, the payoff of all the players, or an equilibria in the game where this is not the case, from my point of view, are not the same and cannot be analyzed in the same way. Okay? In particular, when you have learning procedure, it will change drastically because the interpretation of a move of your opponent will be different whether you know his payoff function or not. Okay? So, and this is quite interesting in the framework of stable equilibrium because what Goldberg and Mertens were thinking of is just starting at property of the equilibrium manifold and deduce property of the equilibrium. But when you have the equilibrium manifold, there is nothing about the fact that you know or you don't know the payoff of your opponent. It's a geometric object. And from this geometric object, you want to deduce property of the equilibrium, like the index or the degree or things like this. Okay? And all this property of information or rationality vanishes. Okay? Related area is signal or conjectural equilibria or so on. Okay? A second topic is the analysis of the equilibrium set. So it started, in fact, the fact that generically the set of equilibria is finite and odd is due to Lemke-Olson. Okay, and there is alternative proof later on generalizing this result to n% gain due to Bob Wilson and Rosenmüller. Okay, and there is a very nice paper by Shapley extending this and who introduced, in fact, from my point of view, maybe among for the first time the notion of index. Okay, and Shapley introduced the index not by looking at the displacement map of some Nash field, okay, but by looking at the determinant of the matrix AB, okay, and following basically the Lemke-Olson algorithm, and he proved that and showed that there were equilibria with index 1 or -1 generically. The sum is always, generically the sum is 1 and the number is odd, okay, and okay, but without fixed point here. And then the next development is due to Goldberg and Mertens, and it's a structure theorem. So it says that for a finite game, finitely many players, finitely many strategy, the set of equilibria is homomorphic to the space of games. Okay, so there is a continuous deformation of the manifold of equilibria to the space of game, in fact, to the graph of the projection map. Okay, and this allows to define the degree of the projection from the manifold to the base space, okay? And then to deduce that the degree is actually equal to the index coming from the displacement map, namely from the use of a fixed of a map from where the fixed point are the equilibria of the game. Okay? So here you have two concepts. One is looking at all games and at the regularity of the projection from the manifold of equilibria to the base space. And the other is giving a fixed game to look at the property of the fixed point map, where the fixed points are the equilibria. Okay? And as soon as this map is continuous with respect to strategies and payoff, then these two concepts, index and degree, will coincide. Okay? And then, so these are the names, the Michaelis and Germano and Govidal-Wilson. And then the next step is to relate this to dynamical properties. Okay? And this is one of the from my point of view, very nice open area. Okay? So the result of De Michaelis and Riesberger was that if a component of equilibria is asymptotically stable, then it has to be the case that its index equals the Euler characteristic. Okay? So, for example, who gave the example of a component of equilibria which is homomorphic to a circle? Say, Rida, you gave this example. Okay? So, in this case, you see that the set of equilibria is homomorphic to a circle. Then, as a component, the index is 1 because there is no other equilibria. But as Euler characteristic is 0, so you see that this set, while it's the only component, it cannot be asymptotically stable. Okay? So these were the kind of. So again, here in all these slides, okay, there is no notion of whether you know or not the payoff of your opponent, whether the threats are credible. Okay? This is a completely different story. A third point is super game. So let's say repetition of game with competitive formation. Okay? And so it basically extends the Folk theorem to sub-perfect equilibria, or there is a huge literature where you have variation on the evaluation of the payoff, whether there will be signal, derivation of the player, and so on and so forth. Okay? And then a related area is perturbation, where you have this famous paper by Krebs, Wilson, Roberts, Krebs, Milgram, Roberts, Wilson, and so on and so forth. Okay? So all these were very, very active results. Okay? And the last topic I wanted to mention is game with a large number of players, so population in atomic games. So basically the first paper I know of is Wardrop, which is an extension of Nash equilibria to a conjunction game. Okay? The main difference with Nash equilibria, I mean, is that it's not that the deviation, so in a repetition, it means that deviation cannot be observed, but here it means that the deviation do not have an impact on the average behavior of the player, okay? Because it's an anatomic framework. Its fundamental is biology and also in learning procedure. Okay? The related area will be mean field games, but I will not discuss this here. If I make a comparison with value, I will describe here 4 fields where there were a lot of recent results concerning value. One is the value operator. So if you look at the map associating to a function, so assume that the function satisfies the property such that there is a value, okay? So assume that you look at this map, and then there are specific properties. First, it's monotonic with respect to the order on F, the number of strategy. It's translation invariance. If you add the constant to F, then you have the constant to a value. It's non-expansive, meaning that the value of F minus the value of G is less than the norm of F minus G for the uniform norm. And this is crucial to derive the regularity aspect, for example, the derived game or the dual games, and to look at asymptotic behavior. And if you think, for example, of the Mertens-Zamir operator, one way to get it by iteration, okay, you start by some function minus infinity, and then you iterate, so you use drastically the fact that this operator is monotonic and regular, okay? So this was value operator. Point 2 is alternative statement. So this is related to what Sergio was saying, that one big consequence of the min-max theorem was calibrating. Okay, you could say here that it's approachability, which takes the form in the convex case. Either player 2 can prevent in one stage player 1 to approach a set, or player 1 in the repetition can approach the set. Okay, so you see there is a duality here, but it's not symmetrical. Either in one step you can close the problem, or okay, so what Sergio proved is the existence of calibrating procedure by using the alternative aspect of the min-max, namely the simple case. Okay, if in one stage you can close the problem, then it's okay. Okay? So, and there are a lot of extensions of this result, for example, to the case where you have signals. Okay? A third topic is recursive formula. So this corresponds to the extension of the recursive structure for zero-sum games due to Shapley. And it takes the form of an operator of function for which the value, for example, of the discounted game is a fixed point of the operator. Okay? So this is, in fact, a general procedure, and you have to find what is the natural state space on which you will express this function. And in fact, it's a set of consistent probability on the universal belief space. So you have a state space, and then there are private information, and then there is a hierarchy of belief, the belief of player 1 on the state space, the belief of player 2 on the state space, the belief of player 1 on the belief of player 2, the belief of player 2 on the belief of player 1, and then you have all this hierarchy, and this is how you construct the universal belief space. And what are the consistent probability on the universal belief space? It's the probability on the product here, such that the conditional probability given the type of a player is actually equal to this type. Okay? And you see that when you prove that, in fact, this is the natural space on which you can write the recursive formula. Okay? And strategy of the player will be simply mapped from the space of probability, regular probability to moves. Okay? This will be the extension of behavioral strategies. So this defines an information structure and allows to compute the transition on the state space. Okay? So what is crucial here is that when the min-max theorem holds, you can assume that both players know the strategy of their opponent. So you can update, both players can update the state variable. Okay? Think of a game with incompetitive formation. Take the very simple case where I am the informed player and player 2 doesn't know. He has some prior distribution on my knowledge, and knowing my strategy and seeing what my move, then player 2 will update his posterior. Okay? But for this, he has to know my strategy. The min-max theorem said it's the same value. So you can assume that player 2 knows my strategy. Okay? So you have this recursive formula involving the posterior distribution and the martingale. And this is crucial to analyze the asymptotic property of this game. Okay? So this is true for all games as soon as you can use the min-max theorem. Okay? And it's fundamental to use asymptotic property, the connection with the Hamilton-Jacobi-Bellman equation, differential game, and so on and so forth. Okay? And the last example will be uniform and asymptotic criteria. When you look at zero-sum games, you have one asymptotic approach, meaning that you know the length of the game, end-stage game, or you know the discount factor, and then for Hn, you know Vn or V lambda, and you look at the limit of these values. And the uniform approach, which will be in terms of strategy, you want a strategy that will be good in all long games. Okay? And in the zero-sum case, if you have the uniform approach is stronger than the asymptotic approach. Okay? If you have strategies that are good in every long game, then it will be implied that the sequence of value converges. And this is not true for non-zero-sum game. Okay? So comments. If you look at all the topics I define under equilibria, namely the manifold equilibria, super games, and the selection of equilibria, in the zero-sum case, it's trivial. It's empty. If you repeat a zero-sum game, the value will be always the same. Selection of equilibria, there is the set of equilibria is exchangeable, and it's a product of convex set. And the manifold of equilibria is trivial, it's constant, and you have convex set, and so on. Okay? So all these four topics that I was developing concerning Nash equilibria are trivial in the zero-sum case. On the other hand, all the topics I developed for zero-sum games, namely value operator, recursive structure, duality result, and uniform approach, are not true for non-zero-sum games. Okay? So the main point will be, let's say, the operator approach. Okay? If you don't have the min-max theorem, you cannot assume that you know the strategy of your opponent. Okay? You have to define your strategy in a repetition of the game on the histories. Okay? You cannot say that my strategy is a function of my beliefs, okay? Because you don't know the strategy of your opponent, so you cannot update the belief. Okay? So it means that there is no recursive structure in general for Nash equilibria. Okay. So all this analysis is completely different. So there are some links. Okay? One link will be through variational inequalities. So assume that you have a smooth concave payoff function. Nash equilibria takes this form, okay? To say that player 1 maximizes payoff at SI. It's equivalent to say that the gradient of his payoff function with respect to the I variable satisfies this. Okay? So if you look at the diagonal gradient associated, you get this equation. And then there is a dual, which will be the min-t equation. This is Nash, this is min-t. Okay? And what is amazing is that if the field is dissipative, namely if you have this property, then the two equations are the same. And here the relation is that dissipative, a typical example of dissipative vector field will be the gradient associated to a zero-sum game. It also applies to, but what means dissipative, you see, it's an inequality that linked the payoff of the players. Okay, so you see that if you don't have connection between the payoff of the player, there is no reason it will be the same. And here, if it's dissipative, then there is equivalence between the two. But in addition, the proof is it can be used through the minimax theorem. Costis has a nice example of using this when you have a game on the graph where each player is playing a zero-sum game with on each link of the game. Okay, so if you look at the overall payoff, then there is these dissipative properties, and then you can prove the existence of an equilibrium through the minimax theorem or property of learning procedure. So the second example is no regret dynamics. Okay, where what you have come proper, if you use no regret dynamics, for example, what Sergio explained, you get that if the trajectory converges, then it will converge to a Nash. Okay? And if the diagonal is dissipative, then accumulation point will converge. The first point, meaning that if learning dynamics converge, it converges to a Nash, from me, it's the generalization of Nash mass interpretation. If you have a dynamical process that will converge somewhere, then it will converge to Nash. Okay? This is, from my point of view, the interpretation of the second justification of Nash equilibria. Okay? Correlated equilibria, so connection with the zero-sum game is twofold. First, the proof of correlated equilibria. Correlated equilibria is, in fact, the set of correlated equilibria is a set of optimal strategy of one player in a zero-sum game. Okay? Because you look at what are the conditions for correlated equilibria, and you see that the condition for an optimal strategy of one player in a finite 2% zero-sum games. Okay? And the second is that if you refine the consistency procedure from internal from external to internal, then the set of empirical distribution will converge to the set of Nash equilibria. So what is the connection with what Sergio was saying? Okay. Correlated means that you need to build something on which you will correlate. And what is the stuff? The stuff is the past history. So you look at the past history, and this is the random information on which the player will correlate. Okay? If you look at stage by stage payoff, okay, you need something else, and this is the fixed point property, which is not here in this case. So just to summarize, value and equilibria are quite different concepts with specific property and field application. They correspond to two approaches that are complementary and cannot be reduced one to the other. Okay? A typical example will be zero-sum games with lack of information on one side. Okay? So it's a K-view theorem. An optimal strategy for the informed player is what is called the splitting procedure. It's defined in terms of strategy. You have a function u, you take the concavification, and you look at the strategies that will generate the martingale that realize the concavification. Okay? So it's completely independent of what player 2 is doing. It's a way of player 1 of using, in optimal ways, information. On the other hand, the optimal strategy of player 2 is basically the approachability. So it's Blackwell. You look at some hyperplane above this function u. This defines a vector payoff, and you will approach this vector payoff. Okay? I don't see any equilibrium property there. You have two strategies. There are two, from my point of view, two unilateral procedures that have good properties, and then it shows that in this case, the V lower bar and V upper bar coincide, but this is another story. Okay? So I don't see the connection here with equilibrium. Okay? Many thanks.
So my question would be, from your viewpoint, since equilibrium, if equilibrium and value are two conceptually separate concepts, what would be the n-player version of value? What kind of generalization would you deem consistent with the two-player version of value? It's a philosophical question, but I'm asking.
This is one answer, but correlated equilibria, it's a set, and it needs to come from some, there is some. Correlated equilibria is basically Nash equilibria of the game extended by some information process. Okay? Where is this information process coming from? Okay, this is an issue. Okay? But in terms of dynamics, I have more example in terms of dynamics. I think that if you look at all dynamics, it's the way one player will react to a sequence of gradient vectors. Okay? He plays something, he got the gradient. And then he plays something, he got the gradient, and so on and so forth. Okay? I think that there are two issues there. First, we shall not look at equilibrium, at convergence. Okay? There is no reason that a dynamical process should converge. We should look more at stable set or asymptotically stable set, okay? Like in the example of Jean-François, or in potential games and so on. Okay? And then this set could be not a collection of equilibria, but the set as a set is stable, okay? Like when you have the equilibria with a stick of, equilibria here, it's not a set of equilibria, but nevertheless, the component is stable. And second, I think this is something very, very complex, but I said that in Nash equilibria, you don't know the payoff of your opponent. I think you should try to get some information on the payoff of your opponent by looking at the sequence of gradients you get in the procedure. Okay? So you should learn, you should get information about whether, for example, in the zero-sum case, okay? You don't have to learn everything because you are already, the other is playing, okay, basically the opposite. But in the general case, I think this is the way it should work. And I think there is a big difference between one-shot and repetition. In a one-shot game, equilibria is fine, but when you repeat the game, I don't see why stable or good learning dynamics should converge to the set of equilibria. Okay? And then there are plenty of alternative solutions, but okay. For example, in potential perturbation of potential game, when you destroyed the set, okay, you know this example, okay, where the maximum of the potential is a set of Nash equilibria, look at a small perturbation. This set is still asymptotically stable, but there is no equilibria anymore, while I think it's natural to look at the dynamics converging to this point, okay? And the Nash equilibria is bad, and it should not be played.